In this last video of Module 3, we are going to look at fossil types, the processes involved in fossilization, and the modes of preservation. But first, what is a fossil? Fossil literally means something dug up. In our usage, it means evidence of former life. Scientists who study fossils are called paleontologists. One of the main areas of study in paleontology is taphonomy. Taphonomy is everything that happens from the death of an organism to discovery of the fossil. It includes the subtopics of necrolysis, the decompositional processes upon death, biostratinommy, the sedimentary history of the fossil, and diagenesis, the chemical and mechanical alteration prior to recovery. When an organism dies, if the dead remains get buried rapidly, it has a greater chance of becoming a part of the fossil record. Exposed remains undergo delayed burial and are subject to biological and chemical processes that could remove the organism from the fossil record entirely. Preservation upon death is the exception rather than the rule. There are three types of fossils. Body fossils, which are direct evidence of life, are actual pieces of the organism, such as bone, shell, tooth, or hair. Trace fossils provide indirect evidence, such as tracks, burrows, coprolites, tooth marks, and scratch marks. Such fossils give information about organism behavior. Chemical fossils are compounds produced by an organism and preserved in the rock record. Stable isotopes of carbon and nitrogen are the most likely chemical fossils to be studied. There are two types of body fossils. Unaltered remains are the original material of the organism that has not been changed to another substance. The fossil may have lost water or color, or the proteins of the soft tissue may have degraded, but overall they are not altered. Altered remains are those in which the original material of the organism has been changed to another substance. There are multiple ways fossils can be preserved. Unaltered original shell material is self-explanatory and constitutes an unaltered fossil. Altered remains, though, can be preserved through several processes: replacement of one mineral with another more stable mineral, recrystallization to the same mineral but in a more stable form, permineralization, where a mineral crystallizes in pores, as in wood or bones, carbonization, where soft tissue becomes preserved as a thin carbon film, and molds, where the original shell is preserved as an impression in mud or mimicked by mud infilling an impression. Encasement in amber preserves unaltered remains, in this case insects, but other animals such as amphibians and reptiles and even a dinosaur tail tip with feathers have been encased in amber. Freezing or mummification preserves unaltered remains. We frequently find animals preserved in permafrost, such as this baby mammoth. She is dehydrated, but other than that, she is unaltered. Forms of mummification in dry caves in cold climates have also produced remarkably well-preserved, unaltered remains. Permineralization occurs when pore spaces within the fossil are filled with a mineral, usually silica. Petrified wood and bones are usually preserved this way as altered remains. Recrystallization is an alteration of the original material into new crystals. In this case, the shell material has altered from less stable aragonite to more stable calcite, which are both forms of the same mineral. Replacement is alteration of remains through replacement of the original shell material with another mineral. In this case, an ammonoid shell was replaced with the mineral pyrite, also known as fool's gold. Carbonization happens during lithification, when pressure and high temperatures volatilize the nitrogen, hydrogen, and oxygen of an organism's proteins, leaving behind a black carbon film. This is an exceptional alteration of soft flora and fauna. Shallow imprints are called impressions. They're common for things like leaves and flat shells. Deeper imprints with a negative relief are called molds. If a mold later fills with sediment or minerals, it will form a positive relief copy of the original fossil called a cast. This is a photo of a shallow impression of a fossilized shell. On the left hand is a mold of a trilobite. Notice the negative relief. On the right is a positive relief cast. The original trilobite material is gone. Trace fossils are indirect evidence of life. Dwellings and structures are fossils not of the organism, but of a structure it built. For example, calcareous tubes that are secreted by some marine worms as living structures. Tracks and trails are trace fossils, but the challenge with tracks or trails is linking them back to a specific organism. This is much more easily done for fossil groups with living representatives than for extinct organisms. This is a photo of burrows. Burrows are typically left by animals feeding or by sheltering in the sediments. These trails are left behind by trilobites. The only reason we know this is that one of the unlucky critters died at the end of the trail. Tracks are trace fossils that can actually give us a lot of information. We can determine the environment. We can determine if the animal was running or walking by measuring its gait. We can often find adult and juvenile tracks together, sometimes entire herds, which tells us about their social hierarchy. What we can't always determine is what animal left the tracks. Other trace fossils that are often left behind are things like gastroliths or stomach stones, often swallowed by herbivores to help digest tough vegetation. The animal on the left died, and the gastroliths it carried remained in place. Coprolites are another common trace fossil. Coprolites are fossilized dung, and as you can see in the photo on the right, they can take on many shapes and sizes. This is the end of Module 3 and the end of our background lectures. Next, we will investigate the origins of life on Earth.